Hello, my name is Ron Terry. I will be the lecturer for a series of discussions that will be presented on reservoir engineering. This course is designed to introduce engineers from many different disciplines to the field of reservoir engineering. Over the several years that I've taught this class at 3 different universities, I've had students from petroleum engineering, from chemical engineering, from civil, mechanical, and electrical engineering all take the class, and they've all done reasonably well as they've been in the course. The reference text that we'll use for the discussions will be Applied Petroleum Reservoir Engineering, 3rd edition, and here you'll see the cover of that text. The 1st edition was written by Ben Kraft and Murray Hawkins and published in 1959. The 2nd edition was revised by myself and published in 1991. And the 3rd edition was revised by myself and a colleague, Brandon Rogers, and published in 2014. So this course will contain a series of lectures developed from this book and from some PowerPoint slides. Following the lectures, a few practice problems will be found in the book. I'll give those to you, and then we'll go over those practice problems in another lecture. And we'll review those before we continue on to the next chapter. To start, the field of petroleum engineering is divided into 3 different emphases. They are drilling, production, and reservoir. We will touch upon drilling and production just a little bit during this course, but most of the course will be on the reservoir engineering aspects. The first thing that I want to address is what oil looks like in the ground, what hydrocarbons look like in the ground before we mine them, before we drill for them. I remember one time going on a lecture and talking at a university, and there was a fellow there that was teaching in a chemistry program who had a vision of an oil reservoir that was like a swimming pool. And if that's the kind of picture that you have for that, we need to eliminate that real quick. Oil is not found, hydrocarbons, oil or gas, are not found in a swimming pool. They're found in the pore structure of a rock. This slide depicts the fact that sometimes we'll have water as an aquifer underneath a hydrocarbon deposit. Sometimes we'll find oil by itself, sometimes we'll find gas by itself, sometimes we'll find oil and gas, with gas on the top of the oil surface. Here is a slide showing the concept of porosity, which we'll talk about in Chapter 2 a little bit more. But here, what I'm trying to show is that the oil and the gas exist in the pore structure of the rock. So again, not in a swimming pool. So if you look at the void space that's occupied in this dish with the marbles, the oil is filling that void space. So it will exist in that pore structure. There are several kinds of rocks that we find oil and gas in. One is a sandstone rock. Here is a picture of a sandstone rock. A sandstone rock is very typical of what you might find along a highway. You pick it up, you throw it in the river, skip it across the lake, whatever. That's typically a sandstone rock. Second kind of rock structure that we find oil and gas in is what we call carbonate rock, and here you can see the vugular nature, the holes in this kind of rock. Those are the 2 dominant types of structure that we find oil and gas in. Let's talk for a minute about how we find oil and gas. It's an application of what we call seismic technology. We have this vibrator truck, as you can see on this slide, and it will send out some energy into the Earth's surface, and those waves will go down, hit a structure, and bounce back into the recording truck. And the waves will bounce back at a different rate depending upon the kind of structure that it's hitting. And we can map out then that structure from getting the waves as they return back into the recording truck. We can map out the structure of the formation then and see if it contains liquid or gas or if it's just solid rock. Here is a slide showing the same kind of thing on an offshore experiment, if you will. You can see the vessel is sending off the signal. There are acoustic receivers that are attached to the vessel that are receiving the sound waves as it comes back to the surface. Here are two types of structure that we find the hydrocarbon in, the anticline or the fault. One thing that you should know about a fault is that it's a boundary where no fluid will flow across that. So the oil and the gas will not penetrate across that fault. And we'll see that in several applications through our discussions. Let's talk a little bit about drilling for oil and gas. I remember one time taking some students on a field trip to southern Oklahoma, and their drilling company was drilling for gas. And the formation was 30,000 feet deep. And they started out with a hole that was 3 feet in diameter. And here you can see a picture that's pretty dark, but you can see two operators working on the drilling rig. This picture on the slide shows the structure of that drilling piece. You can see that it has 3 wheels that rotate as it digs into the ground surface. The drillers will pump a fluid through the casing, and it will pick up the shavings that are dug out from the drilling bit and circulate that back up to the surface. And then it's dumped into this picture depicts a drilling formation, and the mud is brought back up and dumped into this pit, this mud pit, if you will. So that's a little bit about how we drill for oil and gas. Some of the challenges that we see in drilling for oil and gas, of course, are the structure that the drillers are working on. And this particular slide shows the challenges that we might have in drilling for oil and gas in offshore situations. You can see the different types of structure that they would use for the drilling rigs. If we know that, if we have a reservoir that we already know we're producing from oil and gas from it, and we want to develop more wells in that reservoir, we have a pretty good success rate of extending that reservoir on the surface and drilling and reaching a well that will bring up oil and gas. If it's an exploratory well, either in near a reservoir that we know has been producing, our success rate is not as good as you can see in this slide. Many years ago, our success rate was even much less than this. It was 1 out of 7 or 1 out of 11 wells would be successful. I remember a company drilling off the shore of Alaska, southern coast of Alaska, back in the 1980s. They brought in some sand in a very shallow part of the ocean and created a little island. They drilled 3 wells, cost them $180 million, and all 3 wells were dry. So they had no production from those 3 wells. So, but again, today we're a little bit better successful with the kind of seismic work that we're doing now. One thing that has added to the success of producing from known oil and gas reservoirs is the concept of horizontal drilling. And here this slide shows a well where the drillers have gone in perpendicular to the surface. They've reached a point where what we call the pay zone, where the oil and gas exists, and then they turned it at a 90-degree angle and went through then parallel to the pay zone. Here is a picture showing a series of 51 wells that were drilled from one well pad. So the concept of horizontal drilling has really added efficiency to the drilling process and production process. Another concept that has been developed. It's been around for many, many years, but it's in the last 10 years been developed and even more extensively and used more extensively is the concept of hydraulic fracturing, or fracking as it is called in some cases. Here you can see in this slide the driller has gone down again perpendicular to the Earth's surface and then turned the well at a 90-degree angle, and then they will inject a solution of chemicals and rock into the well and at a very high pressure and fracture into the formation, and that will allow then gas or oil to drain into the producing well in a lot more areas than just the typical vertical well that you would see. Here is another picture of the fracking process. You can see that the fluid going into the shale zone, creating this fissure with this high pressure, and then the hydrocarbon coming into the fissure and then into the well. One of the things that we'll do with this kind of a process is use a proppant to keep the fracture open. If they don't do that and they back off the pressure, then that fracture will seal back up and it will be as if nothing ever happened. And so they'll use tiny structures of rock or glass to buoy up this fissure that they've created and keep it open for the flow. Here's a slide showing a typical fracking fluid mixture that are used. As you can see, most of it is water and sand, but there are some chemicals involved in the fracking process. When oil and gas is produced and it comes to the surface, you can see in this slide, they will come into what's called a Christmas tree, and there will be an initial separation of the fluids. The water, the gas, the oil will be separated here at the surface, and then the oil and gas will be shipped off to a plant where it is refined. The hydrocarbons are refined even more, where chemicals are generated like gasoline or diesel or special chemicals in that process. The production of oil and gas is a displacement or replacement process. There are three types of production that occur that we talk about in the industry. One is primary, then secondary, and then tertiary. Under primary production is when we use the formation energy, the natural energy of the formation, to produce the hydrocarbons. Okay, and at the end of primary production, typically we'll put in these kind of pumps, these beam pumps. You might have seen these driving around and looking at oil and gas fields. These are used at the end of primary production to bolster the energy of the formation to help remove a little bit more of the hydrocarbon from that formation. Secondary production is when we refer to as pressure maintenance methods. Typically we inject either water or gas. So in a producing reservoir, we'll drill an injection well, and some of the gas that's been produced from that field, we'll re-inject it and try to keep the pressure high and use that gas then to kind of push against the oil that's there and recover more of the liquid hydrocarbon. Same process is in place when we use water. In this slide, you can see the water injection well, and it's coming into the pay zone and moving through the oil zone and maintaining the reservoir pressure at a higher pressure and pushing the oil then to the producing wells. After primary and secondary production is done, we go to what was called tertiary production, and these are methods which influence either the interfacial or the viscous forces. And so in this particular picture here in this slide is a chemical flooding process where we inject a micellar polymer solution into the reservoir The micellar solution is made up from a surfactant, kind of like a soap that you would wash your hands with. And so think of the micellar solution going into the reservoir and washing the rock surface with this chemical, and washing the oil off of that and pushing and displacing it to the producing well. Another tertiary production process that has been used in the past is what we call steam injection, where we inject steam into the reservoir and let the higher energy that the water that the steam contains to heat up the oil, make it easier to flow to the producing wells, and so thereby we affect the viscous forces in doing that. Typical primary production is in the neighborhood of anywhere from 20 to 30% of the oil, and then secondary adds another 5 to 10%. So oftentimes we'll walk away from a reservoir with anywhere from 30 to 40% of the oil still in place. And so we'll need these tertiary techniques or the horizontal drilling techniques to help produce the oil from those reservoirs. This slide shows a location of world oil reserves. The dark zones on this slide will show the largest collection of world oil reserves. Here's another slide showing the same thing with the dots, the circular dots representing the reserves in various countries throughout the world. As we talk about the resource and the reserves, we should define these words. A resource is what is there. So it's the total amount of hydrocarbon that's in place. A reserve is what can be produced economically. And so there's a big difference between the resource and the reserve. Unconventional liquid fossil fuels are either oil sands, tar sands, or natural bitumen, or oil shale. And we'll talk a little bit about those and the types of resource that might be available. In the text, in Table 1.1, we've talked about definitions of petroleum terms. And this comes from the Petroleum Resources Management System. And there are a lot of different terms for definitions for resources and reserves there that you should be familiar with as you go through this course. This slide shows a change in conventional world oil reserves from 2003 to 2013. And the thing that I want to point out here is if you look on the left, and you'll see the year, the column right next to that is the world oil reserves, and you can see that it's increased every year from 2003 to 2013. There are several reasons for that, and we'll talk about that as we go through the course. Primarily, it is a better definition of what is there, more wells being drilled in those oil reservoirs that exist. So they're able to contact more of the reservoir that's there, more resources being discovered throughout the year. So there are several reasons why these reserve totals keep increasing, but I want you to note that they are increasing and have been for many years. This slide will show you where the reserves are over a series of years. This data was taken from the Oil and Gas Journal in various settings, and you can see that in 2010, January 1st of 2010, Saudi Arabia had the most reserves of nearly 260 billion barrels. Canada was next, 175.2, and then you can see all the others. Notice that in the sixth position on this slide is Venezuela. Here it is in 2012, and look at Venezuela has increased to the second position. And here is 2013, and Venezuela has surpassed Saudi Arabia. And this slide shows in 2014 the same kind of thing. So reserves are being found in countries as we're speaking. Here is a list of the top 10 largest oil producers in the world in 2013. You can see that Russia led the world. Saudi Arabia was next. The United States was next. We'll talk a little bit more about the United States' increase in production over the last several years. Here's a global projected liquid fuel production from a U.S. survey that was published in 2014. And you can see that it's predominantly conventional oil, but you can see that the use of unconventional oil and biofuels is increasing as well over the next 30 years. Here is a slide of showing the major unconventional oil resources from World Energy Council in 2014. This is a slide showing the amount of oil sands. The light green is what's in place, and the dark green are the reserves. And you can see that Canada has a large supply of oil from oil sands or tar sands. Here is this second picture on this slide shows the oil shale. And you can see the United States has a huge supply of hydrocarbons from oil shale. This slide shows a table extracted from the 2010 Survey of Energy Resources from the World Energy Council. And you can see about the fourth column over, you'll see the total original oil in place was about 3.3 trillion barrels of oil from tar sands or natural bitumen. So it's a large resource of tar sands oil. This table, again, is from that same World Energy Council report, and this is showing the shale oil resources of the world. And again, this is like 4.7, almost 4.8 trillion barrels of oil in place. This slide shows the types of reservoirs that will be discussed in this series of lessons that we'll be talking about and that are discussed in the book. You can see on the right-hand side of this picture is what we call a single-phase gas oil reservoir. This is where we drill into the reservoir. We find hydrocarbon in place, and it's at the pressure and the temperature that correspond with point A in this diagram. And it's gas initially, and as we produce from that reservoir, and you need to think now about what will happen to the temperature in the reservoir as we produce. The reservoir is surrounded and insulated really well, and so the temperature is going to stay constant during the production life of that reservoir. And so if you look at this figure, in the reservoir, the path of production will go from point A down to point A prime. And so that's the constant temperature process that we see. And so we refer to this kind of reservoir as a single-phase gas reservoir that stays as gas the entire producing life of the reservoir. Now, as that gas is brought up through the producing wells to the surface, it could very well produce some condensate from that gas. And so there could be liquid oil that would be produced at the surface, but it won't show up in the reservoir. That's the first type of reservoir that we'll discuss, and we'll discuss those in Chapter 4 in the text. The second type of reservoir is that found at point B. Again, initially this is a gas reservoir, or what we call a dew point or retrograde gas condensate reservoir. As we begin the production, as we go down that constant temperature, we reach what we call the dew point at point B1. There, liquid begins to condense out of the gas phase, and we form drops of liquid in the reservoir. Initially, these drops of liquid are not concentrated enough to flow to the wellbore, so they will stay in position until they reach what we call a critical saturation. That critical saturation is typically 10 to 15%. And so a lot of the liquid that comes out will stay in that reservoir until it reaches point B2. And here you see in this phase diagram, it begins to revaporize into the gas phase. And so at this point, it goes back into the gas phase, and that gas phase is being produced through the wellbores. And so we'll collect that liquid again on the surface as it goes through the separators. We'll discuss those reservoirs in Chapter 5 of the text. The next reservoir that we'll discuss in Chapter 6 is the reservoir that we'll find at a pressure and temperature at point C in this diagram. We're to the left of the critical point now, so it's not a gas phase, this is a liquid phase. We call this a bubble point or dissolved gas reservoir. And here there's no gas phase initially, but as we drop to point C1 on this constant temperature production process in the reservoir, we'll reach what we call the bubble point. And here gas begins to come out of solution. And when the gas comes out of solution, it will remain immobile until it reaches that critical saturation that we discussed a few minutes ago, in anywhere from 10 to 15%. And when it reaches that concentration, then it will begin to flow to the producing wells, as the oil is already flowing to the producing wells. And so we'll produce from the reservoir both liquid and gas phase. Now again, on the surface, we'll probably produce gas as that liquid oil comes to the surface and goes through the separator systems. The fourth type of reservoir that we find is one at point D, which is inside the phase envelope. And this will have typically a liquid hydrocarbon and a gas cap associated with it. And so when we drill into the formation to produce from that formation, typically what you'll find is the producing wells will be sealed off in the gas phase and underneath, and just be producing from the liquid phase. So those are the four types of reservoirs that we'll find and that we'll talk about. The fourth type, the one at point D, we'll talk about in Chapter 7 of the text. The last thing that I want to mention in this first lecture is bringing the well fluid to the surface. As we bring that well fluid to the surface, and it goes through this initial separation either at the well or in our separator plant, it'll go through what we call a primary separator, where we will produce some gas and some liquid. The liquid will go to what we call a stock tank, which will be operating at standard conditions. Typically, those standard conditions in our industry are 60 degrees Fahrenheit and 1 atmosphere, or 14.7 psi. From the stock tank, we'll produce more gas and a different composition of liquid. Total, we'll have a G sub P and an N sub P then, a gas produced and an oil produced. And this will go into our sales volumes of gas and hydrocarbons. This concludes our first discussion. We'll start up with Chapter 2 in our next discussion.